All right. So, thank you very much. I mean, thank you to the audience for being here and attending. Thank you, Rainer, for the kind introduction and also, quite frankly, for organizing this. So I can't say thank you enough on the effort that you put into this. So it's great to have this outlet to get together and exchange. So indeed, today I want to talk about the Terawatt challenge and the new materials and interfaces in photovoltaics, or PV. In short, for converting sunlight into electricity. And I'd like to begin a little bit with here this outline or slide that is just derived from our template for the MOPCA conference that is going down in Strasbourg next week. And so we're living on this planet, and question is really on how do we power an electrified planet. So what does it mean? It means that in order to reach high levels of decarbonization, we need to change our mode of our energy supply, mainly to electrical supply. So we see these trends also for transportation, for instance, but this also means that we need to find sustainable and renewable ways to tap renewable sources for electricity generation. And the sun can play a huge factor in this by converting, as I said, sunlight directly into electricity in photovoltaics. So if we look at this a little bit more closely, we like to look at the capacity for electricity generation. On this plot here from Marta Victoria in June this year, we see the global electricity generation in terawatt hours, so units of energy, versus the historical development. It is a bit concerning that most of this comes from coal still, and it's still a little bit growing. What is, however, comforting is that we see a lot of growth also from renewables, and particularly solar PV. So it's a sector with the fastest growth rates for electricity generation. So how can we increase this share of solar for the overall energy supply? Well, we need to increase the installed capacity. So we need to have more panels out in the field that have the capacity to generate electricity. So there we need a rapid acceleration. Currently, the estimate for installed global PV capacity is at 700 to 800 gigawatts. So we are approaching the stated goal of 1 terawatts, but it is also quite interesting to see on what are factors that can play into this. And here I'd like to highlight some economic factors that are driving PV development. In this plot here, we look at the module average selling price as a function of cumulative global shipments. So modules that are actually being sold and installed. And what we see here is this decreasing trend, which means that we get to ship out more modules as the module average selling price decreases. This study was done in 2019 with data from 2015, with a stated goal that if this trends continue, roughly we should get to the 1 terawatts when the module price is at 50 cents per watt. What we actually already reached this price, but we are not quite there at capacity yet. Still, the trend is remains the same. Now there are some limits to how fast and deep we can actually progress in this way. And therefore, I'd like to pull actually some older data from 2013 from the Rocky Mountain Institute. So this study, a little bit tangential, it actually compared the German average residential system price, so how much you have to pay for solar to put it on your roof, with the US average residential PV system price. And main argument was that in the United States it was more expensive than in Germany. But what is now interesting is what was actually the driving factor, maybe still is. And these are the balance of system cost. So from these almost $5 you had to pay, only 83 cents accounted for the actual module, which means that most could be gained by reducing everything around it, but not so much by making solar cells themselves cheaper. So now with these costs going down, yes, the module plays a role again, but keep in mind that the margins are relatively slim and that the price cannot go down infinitely to zero. And with this, we should reevaluate a little bit the knobs that we could turn. So I said it already, we still need to decrease the module fabrication costs, even though there is not much leeway to go. Still, there is some. Then we can increase the module area. Here, however, we are somewhat limited by the space to install all those modules. So there are only so many roofs that you can apply it to. Sure, we are also working on new applications like window panes that are semi-transparent, also integration in cars, for instance, and so on. But you're still limited in using area. Now, one knob that we can turn in our lab actually is to increase the power conversion efficiency, or in short, PCE. This is a factor that gives you effectively on how well the solar cell turns sunlight into electricity, and is therefore just defined as the ratio between incoming solar radiation the electrical power output over the incoming solar radiation. So in an ideal world, this would amount to 100%. But there we are limited through physical laws, and I will actually describe this in the second part of my talk, where we go a bit deeper into these terms, and also what are the actual mechanisms behind it. But for now, if we look at what is the efficiency limit that we want to beat for conventional silicon technology, it's around 30%. So again, we will revisit this a little bit more detailed later on. What we want to get to is to the next generation tandem devices. Here, roughly 45%. This value can vary a little bit, and can, you see reports of up to 47% that are theoretically possible. What is the idea of a tandem device? So it sounds quite simple on the face. So you just you step away from one single cell, and you just take a second cell and you glue them together. And now, however, each cell takes a specific function. So the sunlight, with its broad spectrum of different light at different energies, and the high energy photons will be absorbed in the bottom cell, in cell number 1, whereas the low energy sunlight goes through and is absorbed in cell number 2. And then each of these cells can absorb the light of a specific spectrum part or region in the spectrum more efficiently, adding up to an overall higher efficiency. Again, we will dive into this a little bit more deeper in the second part of the talk, but this is the very basic concept. Now, obviously, you cannot do this with exactly the same cells. So the material that absorbs the sunlight need to have very specific capabilities and need to be made from different materials. And there is where these new hybrid materials that we're working on comes into play. The new generation of photovoltaics really requires the perfection of the interfaces and also the inclusion of new materials. We depart from the classical crystalline silicon and use materials that are part inorganic, part organic here in this Perovskite structure, and build them into these thin film devices. The layer stack that you see here is very thin, so just a couple of hundred of nanometers, which is less than 1/10 of a human hair in thickness. So it becomes paramount importance on how these layers connect to each other, and therefore we need to tailor these interfaces to maintain stability. It is really a huge effort. It has joint developments in the fields of physics, chemistry, material science, and engineering. And indeed, this also pictures a little bit my career path, as Rainer already laid it out, come from physics, but now work in chemistry, but have quite some experience in material science and engineering as well. If you want to have more info on this, however, high-level picture, my colleague Nathaniel Schneider and I wrote a small chapter in this book that came out in Edition CNRS called Economk. So for German speakers, it would be a Wundersame Chemie, or for English speakers, Amazing Chemistry, that just came out this year. All right, this brings me to the second part of my talk, the actual project itself, interfaces and hybrid materials for photovoltaics. And here I'd like to take you on a road delve a little bit deeper into this matter. So before I do so, however, I'd really like to acknowledge a few folks. So first of all, the people who really did the work, or are still doing this work actually. So this is my group on top of PhD students and postdocs at IPVF. In red, you see Claire Baboum and Nitin Malik, who are directly funded through the project. The team at my research unit at IPVF, so first and foremost, Nathanael and Jean-Francois, were also partly financed through the MOPCA funding. We have a lot of collaborations in the French range. Also, I'd like to highlight our collaboration with the Institut Lavoisier de Versailles, where we do a lot of the fundamental studies, but we reach out and work with international groups as well. And so I snuck in this picture here because it's really reminiscent of the time when I had the opportunity to meet you, actually. So it's good to have this community alive and well and in constant exchange. So moving on, this is on what we want to discuss in the next 20 minutes, 30 minutes roughly. I'd like to discuss with you on how we want to overcome the efficiency limit of the single junction photovoltaic device. And then we will look into what are emerging PV technologies and what are the challenges that they still present. And eventually we will turn to current research activities and next steps, where if time permits, I can give you an example of 3 projects run by postdocs that I'm working with at IPVF for their work on interface and surface analysis, materials exploration, and also the optimization of deployment strategies for PV in the field. Now, if I say overcoming the efficiency limit, the real question behind this is really, how do we make better solar cells? So how can we practically get there? And for this, let's have a look at the working principle of a photovoltaic device. So the optoelectronic processes are described in a semiconductor physics picture. I'd like, bear with me, I'd like to go through this in a bit more detail, as it will really make the case on why we select the material, use the material that we that I present later. So what you see here is your physical dimension of your solar cell in a very abstract form. You have one absorber layer where you want to absorb the light, and you have 2 contacts that would then drive the current. And the idea is to shine light on this. Light gets absorbed here. It will generate free carriers. So these are so-called electrons and so-called holes. Of course, the electrons are already in the material, but you effectively free them by giving them an extra notch with the incoming light, so that they can actually move around, get to the contact, and then contribute to a current that will eventually power your device or charge your battery, for instance. Now, this is on how you can see this as a concept in real space. But what it's actually quite useful to go one level more abstract and look at the energy space. So we now have on this axis here the Z dimension. So this is still a cross section through the cell, with the bottom contact being here, then the absorber layer being here, and your top contact being over here. Now, the issue is that on the y-axis we have the energy. So electrons in the material, they are sitting at a specific energy level, and with extra light you can elevate them. So this is very well shown here in the absorber layer, where this dark brown curve or brown bar means this energy level is full of electrons, and this one here, the conduction band, is empty, so there's no electron. And in this steady state, actually nothing is moving, so we don't have current. Now, what is happening if we shine light on this? We'll actually generate this electron hole pair, and we excite the electron into the conduction band. And now these charges are free to move and can eventually move to their cell terminals. You can see there is now a difference in energy between those, and they amount roughly to the voltage. But first and foremost, what it really amounted to is the distance between those 2 energy levels, which we also call the band gap. So, each of this is an electronic band, and there is a forbidden region in between, a gap, so to say, and the electron needs to bridge it in order to become mobile. Now, I said it amounts to the cell voltage. I'd like to go back now and just play with you one thought experiment where we now use light that is not that energetic. So we use low energy photons, in the infrared, for instance. Now the infrared radiation comes onto the absorber layer, tries to elevate an electron, which does not work because it's not enough energy to get one electron from below here to this allowed band up here. And it means that this liberation of carriers is not happening. So you do not generate current. The light is just passing through. This is what makes material transparent, the glass window pane, for instance. And then we look at the other case. Now let's take high energy photons here in terms of blue light, for instance, in the shorter wavelength. This time we can excite electrons above the band gap actually, so they carry extra energy, but this extra energy is actually lost. So they first thermalize to their relaxed state and then go to the terminals, which means you get more or less the same voltage, even though you get more input energy. And this energy is lost due to thermalization that is happening extremely fast and it's very hard to overcome this, but there will be some examples that I actually won't detail out too much. Now, let's see on how we can get away from this with the tandem cell. And there we start with the single junction. So on the left-hand side, you see the solar radiation spectrum. So it's actually interesting to see this also now, present this to climate scientists. For us in the I want to say material science, or for the PV, we are you're oftentimes working only with a black body spectrum that's already enough to make good assumption, but I guess it's a bit more realistic with the different absorption bands given in the atmosphere. In any case, we do have now this broad spectrum at different energies shining on our cell. And as I said, the light gets absorbed, some of it goes through that is not in the above the band gap, and some gets thermalized. Now, if we go, this is what would not go through, was not, excuse me, what it would be, what would not be absorbed but goes through in the infrared. And this part would not be efficiently extracted because of the thermalization. And thus you only use a very small part of the spectrum of the sun efficiently. Now, if we look at the tandem device, there it's a little bit different. On the left-hand side, you see this configuration with the bottom cell and the top cell. Bottom cell, so the top cell is actually a higher band gap shown here. So actually it absorbs light at higher energies. So it has very small thermalization losses for these electrons, but sunlight of lower energies will go through and will then be absorbed in the bottom cell. So over here, this part of the spectrum, again with small thermalization losses. So which each cell you effectively reduce the amount of thermalization losses that you accrue. And there is, of course, a mathematical description for this. It's called the so-called detail balance limit after Shockley and Kaiser. There are some assumptions, not hyper important here. It's only one electron hole pair, you have thermal relaxation, and it's non-concentrated sunlight. But this plot here is actually quite critical, because for a given material with a specific semiconductor band gap, you look at the fraction of incident power. And if you have a high band gap material, this orange part becomes most prevalent, and you can see here in the legend means not absorbed. So this is all light that passes through. And if you make now a very small band gap material, you see that a lot of this here is yellow, and this means thermalized. So you lose a lot of energy to thermalization. And only this blue curve here is sunlight that is actually converted into electricity. In the very ideal case, there are some additional factors that contribute to even a lower fraction of power that you can get out of this. Silicon has a band gap here at 1 eV, giving us about the 30%. And now the workarounds are, as I said, the multi-junction cells. On the left-hand side, you see one of those. This is silicon with a perovskite, a cross-section through these cells. See, there are a lot of different materials that are stacked together in this complex optoelectronic device. A lot of interfaces that actually need to be perfected. And then, of course, there's the assumption of the band gap. So with silicon, it's 1.1, as I said. For the perovskite, in this case, it's 1.6. And you see that now we are in different regimes in this plot here to optimize the converted power. On the other hand, we can think of different means to better harvest energy. So to actually, I don't really see all of my slide. Let me just here we have the kinetic energy parts of the electrons and holes, you see that we usually have this cooling mechanism that leads to the thermalization. But if we turn this off, then we would get very high efficiencies with low bandgap materials. But this is a very complex term. It would mean that we need to tap into hot carrier dynamics and how to extract these hot carriers. Whereas here we, in quotation marks only, look at materials and interfaces. So for the remainder of this talk, we'll really remain in this picture and see on how we can optimize the new materials like the perovskites and the interfaces between the different layers. So, and this brings me then also to the next part, and this is really which is the cell design and material to pick. So let's have a look at these emerging PV technologies that are in the field. And I really want to throw this view graph here at you. It is the holy grail treasure map of every PV researcher. It comes from from ENREL, so the National Renewable Energy Laboratory, where I did my postdoc prior to joining the CNRS and you on this venture in the MOPCA program. What you see here is the best research cell efficiency on the y-axis as a function of historic development on the x-axis. And all these points here are different technologies, and there's a little bit of color coding. So my mouse is a little bit slow, but here you go. And let's go very, very quickly through these. So in purple, you see that we have technology that is already using multi-junction cells since 3 decades. The point here is, and what's different to what we pursue today, these are materials that are very expensive. So you need to go through a lot of hoops and through difficult procedures to make these materials extremely pure so that they function well. What is a little bit more known is this. Oh, are you still there? It seems that my computer froze, but can you?
Yes, we're here. No problems here.
Okay, well, so my computer is really acting up. Sorry, I think I have to very quickly.
Your mouse is a bit slow, but otherwise.
Yeah, okay, so it was actually this pointer. I hope you can still see. Oh, no, it's really slow.
Maybe you could point by saying what you mean.
Yeah, okay, I stick by what I'm just by saying. So that's really not reacting anymore. Let me see.
There was a quick question in the chat. Thermalization loss means simple heat loss?
Yeah, so I mean, eventually you will get to heat. So what you want is the electron to be in this elevated state with a defined energy. And if you can't extract it at this energy, all the extra energy that the electron has will decay to a lower energy. And these decay steps are going into crystal vibrations of lattice vibrations that heat up your material. So yes, the cell gets warm, but you cannot harness it really as electrical power output.
Mm-hmm.
Yeah. So, okay, yeah, thank you very much for this question. So my computer for the moment, it stopped acting up. So let's hope for the best. What I marked here, just very quickly, is the really exceptional rise of perovskite solar cells that jumped really from these 12% that they had in 2012 to now an efficiency of 25%. They are also now taking over the world of quantum dot solar cells, where while I was at ENREL, I helped putting this spot on the on this map as well with perovskite quantum dots. And then also the next step is really the tandem devices where perovskite and silicon solar cells are combined, leading to this 29% over here. Now let me get away from the slide quickly. Yeah, okay, so it was really this slide. Oh, all right, so it is a new class of light absorbers, the perovskite solar cell. I said it's hybrid. What does it really mean? It means that it's organic, inorganic. It is a perovskite, meaning that it has this chemical formula or crystal structure, ABX3, where A is a monovalent cation that can be organic. It can also be some inorganic compound, but the best performing ones use these molecules. B is a divalent metallic cation. And I should disclose here that presently, those that work best are unfortunately based on lead. So clearly we are working on this to get away from this. Tin works as well. We now have very, very active research to work on completely lead-free perovskites. And then X is the halide anion, so the negative charge threefold here in the structure. I don't go through all these properties, but what you can take away from here is that the optoelectronic properties are highly tunable because you can substitute all these materials with slight changes. What is also extremely important is that these materials show a high tolerance for defects and self-healing capabilities, which means if you damage them slightly, they have the capability to go back to their initial form and heal defects so that they still function well. Also means that you can use rather, quick approaches that don't require a high level of precision to make these cells what you make inks out of it that you can print and therefore have printed solar cells. Okay, so what are then the goals and approaches that we aspire to? We need efficient cells. They need to be reliable. So this is one of the points that we dedicate most of our work to, because it's a new material. It means that there are some long-term stability issues that we are still tackling, but make phenomenal progress on this one. And eventually scalability. So it can't be just a small device that you can use in your small appliance, like for a watch or a calculator. No, it needs to cover massive spaces so that we can have upscaling and utility scale power supply. And this again is given by, for instance, the printing technology that I just mentioned. It needs to be integrated into these tandem solar cells. You can see here various examples where perovskites have been paired with CIGS and other thin film technology. This one here I showed already, and eventually people are also working on perovskite tandems. And our point here is to optimize these structures and look into the interface design and tailored interfaces. It gives us effectively a trifecta here of analysis approaches where we do interface spectroscopy. It's a means to look at the surface electronic properties and chemistry. We combine this with photophysics, so how much light gets in, passes through, is converted, and then eventually line this up with the device characteristics. So put it quite plainly, how good is the solar cell that we make with these new interface configurations? There are, of course, a lot of techniques captured in this interface spectroscopy part, but I don't go into detail for this one. I'd rather like to give you some ideas on what we currently do. And I caught this section really, what are the insights from fundamental science that we can facilitate in order to drive this technology? And before we go very much in the details to this, maybe a few words about our institute and where we do this. The Institute Photovoltaic d'Île-de-France, where we dedicate our research efforts on making better solar cells, is a relatively new initiative from 2013. The physical building was effectively finished in 2018. It's a huge collaborative solar cell research platform and functions as a public-private partnership. So CNRS, of course, being a public partner, for instance, so are some universities, but we also work with industries and really have the goal to get output from fundamental science to application in an extremely short amount of time. Also important to have a look at this the scientific program that reflects this actually quite well. So the program one, you can see we have the economy and market assessment. I should actually put forward that it's not just the economy. We are doing full life cycle analysis of solar cells and new technologies even before they are on the market to see, can we, for instance, use specific, certain materials in a sustainable fashion, or do we need to look for alternatives? So there are also environmental aspects that are being looked at. With technical projects, programs that look into these tandems. And I myself and deputy head for the advanced characterization and reliability and modeling part, where we focus on the analysis of these new materials and cells. We have a solar to fuel part as well, and we look into new concepts and breakthroughs. So with this, I wanted to give you a short, insight on how actually our work looks like. So, I'm always a little bit envious if I see pictures from other researchers in the field, really being outdoors and being truly in the field. For us, it actually means being in a locked room with a huge pile of metal where we shoot X-rays on small pieces of glass. So this is on how you approach it. It is small samples for which you probe the internal chemistry and electronic properties, either here with surface chemical and electronic characterization techniques, first and foremost photo emission spectroscopy or XPS, that we do mostly with our partners at the Institut Lavoisier de Versailles, or by optoelectronic characterization on a luminescence platform, for instance, photoluminescence. And here you see the PL, small part of the PL capacities at IPVF. Won't go into detail here on the actual working principle in the interest of time. Rather like to show you some highlights of the work from my group. So Stefania Kakovic is a Marie Curie fellow that I have the pleasure to work with. And her approach was to take a perovskite film, the one that is usually applied or used in a solar cell, and just let light shine on it under controlled conditions, then with various parameters. The clue, however, now is to couple XPS surface analysis with PL imaging, and therefore see on what a change in the surface chemistry, for instance, in the chemical composition and with compositional gradients and so on, how those impact the optoelectronic properties, so transition energies, does recombination of carriers change, and do this for a variation of aging conditions. And if you look at it, you first get these are the different PL images with different light soaking times. We'll begin with a fresh sample, and you see this brightening here, effectively a efficiency increase or intensity increase, setting in already after 10 minutes, but continuing up to 15 hours. We look at these spectra, so these are really spectrum images. So not just looking into physical features, but on how light is emitted from each pixel. And then we can draft maps on the different chemical band gap, so optoelectronic properties, versus the chemical potential. And we see that first we have an immediate passivation. So when you expose your perovskite film to air, it will reduce defects. But then after a while, degradation sets in, and there is a time window in which the material becomes worse and starts to degrade. And with the XPS, we're actually able to really detail these changes. Now, in a second example, we went further into the materials exploration. This was also a little bit inspired by my previous work. So this is an article that I wrote together with Jeff Christians, who's now professor at Hope College, used to be at NREL, where we were both postdocs. What Jeff did was phenomenal work on optimizing the interfaces in this device state. So I said it already, and I showed you many of these pictures now, layer on layer, and Jeff took each layer and substituted it with different molecules, for instance, but also different oxides. And we were able to make solar cells without any protection that worked for 1,000 hours under operational conditions. And this was really new. If you would have asked us 2 years before, we were not even half as optimistic to get to something like this. And however, what is really missing in order to finalize these kind of research is to get a detailed view on the chemistry for the perovskite degradation. So yes, we pull all these different levers and turn the knobs, but can we do it in a more targeted way? And therefore, we need to explore the material properties. And so this is Davide Cerati, who's also Marie Curie fellow with us. If you will be at the Strasbourg conference, you've also the opportunity to meet him. He will join me to be there and talk with you about chemistry. We start at the photoabsorber really. So the perovskite itself is very complex chemical structures, a lot of things that can break apart. And indeed, there is an inherent redox chemistry that is linked to ion migration and degradation into the dihalides. And this is what we look at, complex chemical reactions, where we here in a vial mix the different components and see that if we mix amine with divalent lead, we can get the soft lead amine bonds that will then fully form lead amides. That is a very unstable compound, thereby releasing actually also a hydrogen. Now, it also means that in these materials, there are a lot of protons around, something that was not really considered before, and where Davide takes a deep dive into how proton chemistry will change the solubility, nucleation, and reaction, but also serves as recombination centers or lead to changes in the other optoelectronic properties. If you want to really learn more about this, I can also recommend you a little bit of read here. This was done 2 years ago. We finalized this chemical review, so it's about 70 pages actually on what are the different interface chemistries that we can expect in perovskites and how to circumvent them. And if you want to educate yourself more on photoemission spectroscopy for this, we just finalized this review article last year on photoemission spectroscopies for perovskites. All right, in the last 3 minutes, a very quick example on how we go beyond this. So we had materials exploration, but what do we need to consider when we have these new materials and set them into a solar panel on your roof? What are ideal scenarios for deployment strategies? And here I'd like to put a highlight on the work from Pilar Lopez Varo. Pilar looked into the effects of the local weather on the annual energy yield. And the energy yield gives you effectively the total energy output from a solar module. And of course, you can draft an ideal case. You have your efficiency. You know roughly what's the average amount of hours of sunshine the cell will see, and you're good. Maybe you even factor in some shading due to average cloud activity, and you will get a first estimate. Now, however, there is another factor. A solar cell does not exhibit always the same efficiency. Sometimes, or actually for these new materials, we also need to consider temperature. So a different temperature will change on how well these conversion processes of sunlight into electricity take place. So questions, can we model this temperature behavior for the electron yield? And this is what Pilar did, taking many different points into consideration, also wind convection and different scattered light, and building this wholesome model where she starts with the meteorological module and drafts the solar cell with 3 modules, so an electrical module and optical module. These are really the operational parameters. To be quite frank, this is something that a lot of people also do. But what is really key here is to add a thermal module to see what is the thermal budget on the cell and how does it actually affect the efficiency. And so we don't go into detail here and go into every layer, but what you see on a general scale is a set of the different layers in the cell. So your perovskite, your glass supports, your electrodes, and she builds a thermal model that has an electrical analogy. So here now temperatures are potentials from ground, sky, ambient, and so on. And the heat flow is the current flow. And you can now evaluate these parameters and see that, for instance, the glass plays a huge role in the heating of the perovskite solar modules. Went a step further and evaluated this for different locations of deployment, from Paris to Granada. So we stay in Europe, but cover quite some geographical spaces. And now the real difference is here between this purple bluish curve, the energy yield, versus the these curves where the thermal module has been applied. And you can see that the energy yield under realistic conditions is actually smaller than what you would expect first. And it's important to keep these kind of things in mind when we put a new technology on the market, to understand on what is the expected outcome, and also then improve the modules on an individual basis. All right, so this brings me to the end. This one is for YouTube. If you are interested in seeing what was our publication output and want to follow specific work. And I come to my last slide. It's an exciting journey. Photovoltaics show rapid growth for electricity generation. We need new materials for this new generation of solar cells. And I am really confident that we can derive critical guidelines for the technology development from doing basic science. Now, I'd just like to put a highlight on these contributions. So there is more research on PV in the MOPGAP project program. So, for instance, by Ludmila, who couples this to storage devices, and we will hear from her in 2 weeks. And actually, I'm also very glad that we started a small collaboration as well. And then Yu-Tsung Tsai at HZB, who works on a new concept of solar cells. So thank you very much for your attention, and yeah, I'm happy to take further questions. Thanks.
Okay, thank you very much. That was excellent. Yeah, first of all, I would like to say that that I'm really happy to see this. Also to see that if many brilliant scientists work on such an issue, that solutions come out. I think that's maybe also an important point to raise, that this technology is still in development and will probably still get better. Okay, everyone, you can ask questions by using the Q&A tool, by raising your hand, or by typing your question also in the chat, and I will read it. And yeah, maybe my first question is, I've seen something about, okay, now in East Germany, or in some regions in Germany, you have huge photovoltaic farms, which even are to some extent problematic because they take over area which might be more useful for other things. So, and there I think your research then is also important, like saying, okay, we can put it on human structures anyhow, so don't waste nature. So yeah, but what is the calculations? How much area do we need to cover with photovoltaics and to reach the energy consumptions we have?
Yeah, so I can't give you the exact area. So I mean,
or put out differently, would photovoltaics be enough, or can you what level can we reach in terms of energy supply with only covering the earth with photovoltaics?
I don't think just relying on photovoltaics will be enough, particularly not in the short or medium term. Photovoltaics bear a huge potential. You need to cover only, if you look into desert spaces, for instance, you don't need to cover a lot of unused land in order to generate a lot of enough electricity. So the land use can be, is not the main issue really. Locally, it can be. So, and this I think is the example that you take from East Germany. There are also other factors. So first of all, PV is the good part is you can decentralize it, right? You can set up solar panels in remote places. It plays into your grid integration, which also becomes even better on how to manage these different energy inputs. So I say, A, it won't be, the land use will not be the main issue for PV. And then B, however, is it the only technology that will lead us there? I don't think so. It is a small gear, but we need more. We need also wind, hydro, other sources. And unfortunately, we cannot flip the switch and move everything to PV right away. But with this better technology and the higher share, it will grow, and it will grow faster. When is exactly a takeover point? I don't know.
Maybe one more question from me. How much is like you said you want to get rid of lead, for example, because of course it's toxic and you shouldn't. It's not good idea to use it in material anyhow. So how much is that part of the design strategy that consider also how the materials can be recycled, for example?
So again, the recyclability is what I mentioned in this environmental evaluations that we do. It is. So this is a very delicate, quite excellent question, actually, because yes, we look into ways to recycle the material. It's the problem is not really that you can't do it; it's rather on how much it costs. So then that becomes economically not feasible, and this gives away incentive. And I fear that this is then not the good way to go about it. There are some sequestration strategies where you use additional layers that would make the lead that is in there harmless. We should also start to say that the amount of lead in there is really minimal, right? So these are extremely thin layers, but nonetheless, you don't want to have this anywhere, near environmentally sensitive environment, habitats. So sequestration alone is not enough. So we need to push for these lead-free compounds as well. The tin now becoming better and better. Where there are some examples where we use germanium, but they are in early development stages. So my guess is in short term, the sequestration will be the most important part. And after that, the lead-free will substitute completely.
Okay, we have a question by Chen Wang.
Yeah, hi. Thanks for the talk. It's really fascinating. But I saw there's an increasing discussion on the, it's all the renewables from wind to solar. I remember the MIT Energy Initiative wrote a serious review. So for photovoltaic, if I remember correctly, they indicate that there's a serious limitation from certain minor materials in the future. Because if you really implement in a large scale to meet a very high demand, because the energy is not a small number. If you put any format of a renewable. And we had some colleagues recently came here to do a talk, the more serious economic model. They both indicated to these limitation on available materials. I was just curious because if I remember correctly, MIT report did indicate a future maybe new material can overcome this. So I was just curious. I mean, it's a really novice question. So do you can you enlighten new material might solve these limitation, which is given by the Earth actually?
So yeah, I can. Thank you for raising this issue. Solar in general, the materials are rather abundant. So if you go for classical, for instance, it's based on silicon. So silicon is I guess the second most abundant material that we have. So for this part, the absorber itself is not the issue. It is again part of this not just the life cycle analysis, but also the economic assessment about the scarcity of materials. And it becomes, particularly if you look at the European PV industry, an issue in terms of supply chain. So how much of the raw material actually can we supply here? Also one under fair conditions. So this is also important. What I presented you here, the technology is not working with scarce materials. So you don't need any rare earth or comparable compounds at all. So using earth abundant materials is always at the core of our mission here. I would need to see the report that you're citing in order to discuss with you the details on what might be scarce and what is not scarce. Generally, what we work is considered earth abundant materials. So that's what I can say. Probably rather local issues where supply chains are not provided in a framework, for instance, in the European Union, where we have to import. This is what I see as a bigger concern.
Yeah, thanks.
Okay, further questions? Maybe I have another one. Okay, there's a goal to reach high efficiencies. What do you consider as like the top you can reach, or what is? I mean, at some point it will get more and more difficult to reach very small increments. Does it make sense at some point, or do you have a, so to say, is in the field, do you have a limit that you want to reach, and then everyone would be happy?
Yeah, so no, we actually want to go higher and higher, because this is, I mean, every a percent point of efficiency that you can raise means you can at this, you know, if the costs remain the same, it is an economic incentive, and every economic incentive means you get more of this of solar cells integrated, and more on our energy supply changed to a carbon neutral way to harvest energy. So there is no real limit to it. But we once formulated a goal that we want to be at 30% at 30 cents per watts by 2030. So, you know, makes a nice 30 cube. But I think we have to raise the bar here a little bit. So we want to be well beyond 30% with modules in the field, and this is only doable with this tandem technology that I just mentioned. If we get something on the order of 35 by mid of the 20s in a module in the field, I mean, this would be fantastic in my point of view. But yeah, now I put a bet on the table, it seems. So let's see.
Mm-hmm. Are these techniques used, or it's already, are they in the market, or is it all silicon single cells?
The overwhelming part in the market is silicon, and it is it is quite funny, because even though these techniques or these new technologies becomes more mature, the growth in PV is just so large that that we're just I shouldn't say flooding the market, but I mean there's just the most growth in silicon, because it's presently the most reliable and well-known technology. And so, you know, I don't frown upon installing silicon solar. It's just that we can even do better. And there is in East Germany actually a company, Oxford PV in Brandenburg, that has started to produce perovskite silicon modules. Can't actually relate if they already have a a product and a catalog or something like this, but they are a serious player in bringing this technology on the market. And there are other small startup companies. I know of some in, for instance, at the US West Coast, in some of the industry projects that we work with here, we are looking into valorization routes, so bringing the technology on the market. So it is happening, but if you want to put this on your roof today, or me, if I wanted to put this on the roof today, I think we have to look hard. So this you can't buy it in Obi, for instance. Yeah.
Okay. Yeah. And do you see? But you think it will at some point take over also the large-scale facilities, or is it more that you might expect it more on the roofs of cars and things like that, more a distributed deployment?
So I would hope for the two. I do see that it will be quite applicable to some niche applications. So one big advantage of this technology is that you can print it on flexible substrates, and therefore you could even integrate it into textiles. You can put it on a tent, you can integrate it into cars, and so a car, if you need to spend a few €100 more in order to also get some additional, higher quality solar cells, or not even a couple of €100, then it does not change so much the value of this object, or excuse me, I want to say it does not change the price of this object in total so much. So these niche applications, I see this enter this market much earlier and easier. Now, when it comes to utility scale, we need to see. This is highly dependent on how well we can make good on the promise to have it as a scalable technology. when I say you can print it like a newspaper, that is true, but then you also need, it's still an optoelectronic devices, so you need to make sure that it's free of defects and reliable, and this can be done. But you need a lot of tests first before you scale this up, and then you do this upscaling. You know, you first have your small device, and you try the device that's 10 times bigger. Then again, a fab line that can produce 10 times more, and so on. We are engaging in this process. So, particularly one of our industry partners here, Électricité de France, is in charge of the main driver for the perovskite silicon tandems at IPVF, and are exploring printing of perovskite modules. So I find it amazing on how well industry is advancing on this. Let's see on how quickly we can get a everyday's or something that you can buy on the market out of this.
Okay, excellent. Any further questions? No, maybe I have one more from like biologist in me,
sure.
Which I am. What about, there was some talk some weeks ago about artificial photosynthesis. Did you, I have no idea about it, but do you have an idea about it? And do you think it is a competition to you?
It's a fascinating topic, and it comes to these solar fuels that I showed earlier, and you can think of artificial photosynthesis. You can think of water splitting, where you generate hydrogen, and interestingly, at the core of this, you always have the well, in this case, the photocatalytic material, which has a very similar setup to the solar. So I'm looking forward to the artificial photosynthesis technology to become more mature, and then see on how it competes with PV. But I'm to put it quite plainly, I'm not married to either. Which one is more? And I could imagine that in specific regions, one would work better than the other. If you need to. So, for instance, one issue with PV is that you generate the electric energy, but how do you store it? Ludmilla will show in 2 weeks on some ideas on how it can be done. But with the artificial photosynthesis, you get a fuel out of this that you can store easily. So in maybe in some more remote regions, it could be more reliable to do that. Maybe you want to use a mix of those. There's also solar thermal power, where which is, for instance, where there are huge plants in Spain, or for instance, that are also in parentheses competing with this technology. We need these type of baseline analysis, which technology is best suited for a specific region due to the meteorological factors, but also local supply chains and the energy grid. And find a good mix between all those. That's what I really want to what I want to see going forward.